I thought we'd start today with a few announcements so you all have a sense of how the rest of the final stages of the semester are going to unfold. I had to change my office hours for today from 1 to 2 to 2 to 3. So I will be in the Student Learning Center today from 2 to 3 and can answer any questions you might have on your homework, which is due by 5 today, and 395 Evans, or any questions you might have about your projects. So on Friday, the class time will be dedicated to assistance with your posters. So please come with questions about your project, your analysis. I'll just have my laptop open and we'll take questions. And if you want to upload any poster in advance to BSpace or send it to me by email, we can take a look at that on Friday, or I'll just answer whatever questions you might have. So today's the last day of any new material for the course. And so I'll extend class or this poster assistance on Friday to go from 9 to 10:30. There's going to be no formal class meeting next week in RRR week. However, there is our poster session. I'd like you to arrive between 10 of and 9 o'clock so that you can set up your poster in the Student Learning Center. It'll all be ready for you to unroll your poster, which you'll have on beautifully printed in color on paper. And we'll have an hour poster session, and there'll be more details about what you'll be doing. It's half the time you'll be standing by your poster, presenting your work to the rest of the class and to Harry, Wayne, Mike, and myself. And the other half of the time you'll be circulating around, having bagels and cream cheese and talking to the other people who are standing by their poster. I was going to have a formal review session this coming Monday, but I thought that's a long way from the final exam. And so I've moved it to the following Sunday, December 12th, from 3 to 5 in room 340 Evans. So Evans might be locked at that time, and so it'd be good to arrive. I'll be down there at 3 o'clock to let you in, or a few minutes before 3, and then after that we'll post a note or have people run down occasionally to check to see who's might need to get in, or have someone else's cell phone number to call up to let you in. Our final exam is on Thursday, December 16th from 7 to 10 p.m. And that final is, it's not cumulative. It's going to be based on the material from the midterm to the rest of the semester. I'm really working at getting an exam that's going to be about 1 hour in length and give you the full 3 hours to do it in. But it's essentially like a extended second midterm. And office hours for next week and exam week will be posted on BSpace. That'll be Harry, Wayne, and I will post our office hours. Are there any questions about this sort of final wrap-up? Dan?
So you said that the poster was due, the rough draft was supposed to be due Friday?
Yes.
And what exactly do you mean by rough? Like how?
It should be in the template, and it's considered your homework assignment. So what I'm going to spend the weekend doing is sort of grading your poster and giving you feedback. So I'd like it to be nearly complete, and meaning all the pieces are there. And if you want to put little caveats on it, such as I'm planning to fix up this picture or this figure, it'll look like this when I'm done, so that you've got all the pieces there, but they might not be the most beautiful yet. You can let me know with little footnotes or whatever. Is that so? Please read carefully the homework number 8 assignment. It has full instructions about the poster templates there. It's a PowerPoint. It's all set up to be the right size, and it's got instructions in it about how to put stuff in it. Also, please read carefully the report guidelines so you can know what it is that is going to be in your final report and all of that stuff. Tyler? You? Okay. Adrian?
Do you expect each group member to contribute a draft so they can contribute content?
Each group member must contribute a part of the data analysis. That's in the report guideline.
Right. What is the data analysis?
That could be summary statistics that you have written into a paragraph form that is connected to the overall analysis, or it could be a plot, or it could be a fitting a model and interpreting the results. They don't all have to be figures. Right? But it's really important that your whole group, and this Thursday as tomorrow, you are to go to your section, your team section meetings so that you can all sort of map out your poster together as to who's putting what there and figure out, because there's only one poster, about how you're going to sort of orchestrate that. If it's, I'm not quite sure, I've never used the Dropbox for students in the class I think you all have a Dropbox, right, in BSpace? That's one way to share materials if you find it useful. Other questions? Yes?
For every plot that was put on, do you expect like a plot, caption, and the paragraph, or is it going to be like plot, caption, and
On the poster?
yeah?
Plot with a caption. So the poster should not have a lot of language in it, but every plot should have basically a caption. So you're not going to have a lot of written text. It should be sort of what you might think of as bulleted, formatted text, and even your caption is probably a more abbreviated caption than what would be in your paper. Because you've got only so much real estate, and you want it to be really attractive visually and still tell your whole story, but not have a lot of, small text that's really hard to read. Yes?
What would you say more or less is the ideal number of plots to have?
Really depends on that project. Some people's projects don't have a lot of options, like the space debris folks don't have a lot of options for what they can put. The spam people have so many plots that they could put, so if you want to talk to me during office hours or after class, I can, but that's the point of the Friday thing, is that I can give you some feedback. Other questions? Yes?
Are we going to give the final paper along with the final poster?
Yes. Yeah. Right. Yes. If you all want one more day to do it, that's okay with me, if that would be helpful. Like, hand it in the next day, that's okay. Yes? Okay. So we can have it then you'll have to do it through, I want a hard copy as well as an electronic copy, so it means you'll have to come to Evans and drop it off. But you can have till Thursday if you want. Any other questions? So do remember that poster, the reason why the poster draft is due Friday is so I can get you feedback over the weekend, because it actually takes time to get these things printed. Given our poster session starts at 9 Wednesday morning, you really need your poster by 2. Most of these poster places, unless you want to pay a huge amount of money, these poster places need it the day before, which means you've got to get it to them by Monday. And the particular company that I put on BSpace says that they have no extra charges for rush, and but they do first come, first serve. And so it would be good to get them your poster by Monday if you wanted to pick it up by Tuesday. And you can do it all online. You don't have to go there to turn it in and then go there to pick it up. You can simply, they've got a web format or web form where you can upload your either in PowerPoint or as a PDF. You can upload your poster electronically and then go and pick it up. Any other questions? All right. Yes?
Just when is the paper due with the final or the poster session?
It was the poster session, and we just said we'll have it due the next day.
Okay.
Right. Okay. Here we go. So there are two final topics that we're going to discuss. One is the relationship between categorical variables, and some of you are already working on these kinds of relationships, looking at how one factor, if you will, in R is related to another factor. I picked an example from the spam. So here we've got over 5,000, nearly 6,000 email messages. They've been categorized as spam or not. So that's one variable. That's a categorical nominal variable. And then you also have the lots of other variables. One in particular that I thought I would look at is the is_re. Is this an email in response to a previous email? And again, that's another categorical variable that's nominal with two levels, either yes it is or no it is not. So you might want to look at we might want to look at the relationship between those two to see if knowing that something has an RE in it, is it more or less likely to be spam? So one kind of plot you can make with this, given that we've got two categorical variables, is a mosaic plot. And notice that the RE variable is being cut vertically, and it's logical, true, false. We see that if we look at the fraction here, the fraction of emails that have an RE in it in the subject line looks like about roughly a quarter of the emails. But notice that of those that have RE, very few of them are spam. Whereas of those that do not have an RE, the proportion of spam is quite large, nearly not quite a half. So that looks like that could be a very good variable for use to predict whether something's spam or not. But in addition to that, we could also ask a question of, knowing an email has an RE in the subject line, does that increase or decrease the chance it's spam? It looks like it really decreases the chance in comparison to the overall. And we might want to formally test that. So you can think of this as sort of two variables. One is it spam or not, and the other is it is an RE or not. And so you can see here the table that comes out of R from the table function that counts up how many of each type within the categories. So REs across the top. True is yes, it has an RE in it. And you see that there are only 43 out of the 1,870 or so emails are spam. If they have an RE, in comparison to those that are not, is roughly sort of, it's more than 1/3, 2/3. So here's the formal table, and we could ask the question, this is the same information, but I've now given you row totals and column totals and the overall total. And we could ask ourselves, well, is spam and RE, are they independent? Remember, so this gets back to the notion of probability. You can think of it as you've got this 5,762 email messages all in a big pot. And if I were to sort of pick one out and say, well, what's the chance that when I pick something out, it's spam versus ham? You've got a certain probability you'd associate with that. What's that? What's the chance that if you have all of these 5,762 emails written on little tickets in a box, and you reach in and you draw one out at random, what's the chance you get a spam email? $14.75 out of what? No. Out of 5,762, right. So of the total, there are 5,762 emails or tickets in the box. When I draw out one, the chance I get a spam is 1475 over 5,762. On the other end, I could say, well, what's the chance I pick an email that's got an RE in the header? And that would be 1872 out of 5762. So if I then ask you the question, what's the chance? So we've already figured out what's the proportion of ham or spam, and that was looking at the ratio of the total number of ham messages over the total, or the ratio of the number of spam messages over the total. And we could compute all of those four ratios for ham versus spam and for is there an RE or not. And those are the proportions. 74% of the email is ham and 26% is spam. And then of all of the emails, 68% of it have no RE colon or whatever in the subject line. So when we ask the question, is spam and is RE independent of each other, we would be saying, well, what proportion of spam and REs would you expect in the emails? So in other words, if I were to reach in the box now and say, what's the probability I get an email that's spam and has an RE on it as well? How would you answer that? Yeah? 0.26 times 0.32. And what are you assuming? Yes, that would be one way to do it. And what are you assuming when you make that calculation? The proportions stay the same whether you're in the RE or the not RE. So you're assuming independence between spam and whether or not there's an RE in the subject line. That's right. And so we can test that assumption. So it says, hey, this is sort of like, well, what's the probability I get a spam? And that would be 0.26. Given I got a spam, what's the probability that I have an RE? And you say, well, it doesn't matter, so I'll multiply that by 0.32. So this is figuring out a probability of something and something else is the probability of spam, and RE is the probability of spam times the probability of RE given spam. And we're saying that if they're independent, then I don't have to, then the probability of RE given spam is the same as just the probability of RE. And so we can multiply those two. So yes, that's under the assumption of independence. So what we can do is we can compute a table of counts under the assumption of independence. So what would we expect to see if they were independent? So we can fill in these question marks to give an expected or create an expected table of counts, and then compare that expected table of counts to the observed table of counts. So knowing that probability that you just gave me of spam and RE is the product of 0.26 times 0.32 under the assumption of independence, how would I fill in that entry of spam and RE? That question mark, that's the lower right. How do I fill that in? Yes, so I take the total, 5762, and you did the calculation. Right, it's 0.08 is the product of these two. So it's 0.08 times the total. And I can fill in the whole table that way. So here's filling in the top left is the total, 5762, times the chance it's ham, times the chance that it has no RE. There's 5762 times the chance it's spam, times the chance that there's no RE. And we can fill in the whole thing, and this is what we get. Now, because we're dealing with these probabilities, we're not getting actual realistic counts. There's no way that we would see 479.2 actual emails, but we would still think that our observed counts would be close to what we expect to see. So then the question is, okay, let's compare these two tables. On the top is the table of observed counts. On the bottom is the table of expected counts, under the assumption that there's independence between those two characteristics. So there's a hypothesis test sort of lurking down here, right? There's a hypothesis test that's saying, I'm going to assume that these two variables are independent of each other. Once I make that assumption, I can then create expected counts. And now I've got my observed, and I see they're different. So take a look and see, where do you see sort of big differences? Yeah, you see here in spam, this one right here is 4792, and it's only 43 up there. And this one's 995, and it's 1432 in the actual observed. So what we'd like to do is come up with a single statistic that combines all of those differences into one number, where the bigger it is, the larger the difference between the observed and the expected counts in our table. And we can do that with a chi-square test statistic. So again, the null hypothesis is that spam and RE are independent. Any deviation between what we expect and what we observe is just due to chance variation of this chance process. The alternative is that the difference is real, and spam, in this case, would be negatively correlated with RE. Here's our test statistic. We compare our observed to our expected. We look at the difference, square it, divide it by the expected, and add up over all the cells in the table. So the actual calculation takes, if we look at the bottom right one is 43 is the observed, minus 479.2 was the expected, square it, divided by the expected. We add up all the way across, and we get 790. That's a large value, but again, we need to know, well, is this really large or not? We could simulate the process, or we could apply the null distribution of the test statistic, which is a chi-square. And it's a chi-square with 1 degree of freedom. 790 is huge. The p-value is less than 1 actually in a billion. And so we would reject that hypothesis and in favor of the null, that there is a correlation between them. And the next thing we could do is we could sort of tell from the table, but we could also make a residual plot. That's like, okay, where do we see these big differences? So that's taking each of the terms in the chi-square and unsquaring them. So we get the observed minus the expected divided by the square root of the expected. So in other words, we're looking at those deviations, but when the counts are really large, we're normalizing it by the square root of the count. That's similar to that law of large numbers idea, is we expect that sums will have a larger variance or a larger spread when they grow like root n. And so we're kind of normalizing it so because to put the differences in perspective. So, but we still see, even normalized, that the large residual here, large negative residual, is at the spam-RE combination. And that says there are far fewer spams with an RE in it than we would expect to see. And that's that big negative residual. So we only have 4 residuals, and those are the 4 that we get. Other questions on that? No?
Will you title that standardized residual or just residual?
With a chi-square test, I think people don't differentiate too much between whether they call it a standardized residual or not, but technically, yes, it's standardized. Any other yes?
Go back 2 slides to your alternative.
Yes?
One more. When you said that the spam is negatively correlated, that's almost implying one tail, that chi-square is 2 tails.
Right. So the chi-square. So I'm bringing in what I've already seen from my data. So yeah, chi-square is only 1 tail because you're squaring everything, and so you're going to see large deviations. Large deviations can mean even here negatively correlated doesn't really make sense actually, because these are not ordered. And so there's an order implied. And so let's just say spam is correlated with RE because there's not a sense of direction here. Right. Right. That's a good point. If they were ordered, then that would make more sense. Right. Any other questions? No? Okay. I just put this here so that you could look at it later if you wanted to. I don't want to go through it all, but it's all the code that you would use to take the table and create the chi-square test and make the residual plot. So there was nothing special about those 2 variables being categorical with only 2 levels. You can do this with any pair of categorical variables that have many levels. And you just have a bigger table. And so you can still ask the question, is the variable for the row dimension independent of the variable for the column dimension? And you can still compute your observed minus your expected squared divided by expected for every single cell in your table. It's just more calculations. Notice that basically we were getting those probabilities by looking at the row totals and the column totals and using those to create proportions, and that determines our expected. So nothing changes. The only thing that changes is that the chi-square test has a different number of degrees of freedom because you've got more cells in your table. And so your degree of freedom is the number of rows in your table minus 1 times the number of columns in your table minus 1. And so in our 2 by 2 table, that was 2 minus 1 times 2 minus 1, or 1. In general, it's I minus 1 times j minus 1. This notion of a chi-square distribution for the null distribution, or yes, for the null distribution for our hypothesis, is an approximate distribution, and that typically holds when the expected cell counts in each of the tables are 5 or more. But you also know you could do this by simulation as well and get the sort of exact distribution. Okay, so that's the end of the first topic. And now let's go on to the second topic, multivariate regression. So I'm going to back up a little bit to go to when it's a couple weeks ago that we started looking at birth weight of the babies in the Kaiser study, and we're asking what's the single best predictor for birth weight. And so we were comparing the mother's height and the father's height and the smoking status, and we're looking for the linear relationship between those two. We're comparing the scatter plots and the residual plots, and we were comparing the root mean square error of the regression line to see which one reduced the variability in birth weight by the most. And we found that smoking status in particular reduced the variability in birth weight by the most. So it's not how tall the mother is or how tall the father is. It was actually whether or not the mother smoked. So again, the problem was, do we want to predict birth weight? We were comparing the root mean square error for these various variables. And the smoking status was qualitative. And what that meant was that for every group, for every level of the factor, we're fitting means of birth weight for that group, and then comparing the SD within each of the subgroups to the mean. And the R gives us a total RMSE error for all of the combined groups. So if we look at the question of birth weight and mother's height, the model that we're fitting is BWT as a birth weight on height. That's mother's height. That's saying, I want to express birth weight as a linear function of mother's height. When you do this in R, it gives you back the best fitting line according to least squares. And that is BWT, birth weight, is 26.6 ounces plus 1.4 ounces per inch times height in inches. So the total number is going to be in ounces, and then there's some error associated with that. That error, so what we're getting is an approximation or a prediction for the average, and then we know that there's variability about that regression line. So how do we interpret the 1.4? Remember the coefficient, the units of that is inches per ounce. And so essentially that says for every 1 inch in mother's height, the babies on average weigh 1.4 ounces more. Okay. So what about mother and father's height together? Because the baby is determined by the genetics of both the mother and the father. So why not include both of those in our prediction for baby's birth weight? So we can do that by looking at the two variables, the mother's height and the father's height, together to see how they predict the baby's birth weight. So in R, that's really simple to do. We just say birth weight is a function of height plus mother's height plus father's height. And out comes from R, out comes a fit, a least squares fit. And we're going to talk a little bit about what this means. So it says 9.2 ounces plus 1.4 inches per ounce times the mother's height plus 0.3 inches per ounce of the father's height. So for each group of mothers, so what does this mean? How do we interpret this? So what we do, a way to interpret this is to say, I'm going to look at subgroups of mothers where the mothers are the same height to the nearest inch. So that takes so for example, if we have mothers that are 60 inches tall, I can plug in the mother's height there, and I get 9.2 plus 1.4 times 60. Okay? And that would turn into, what, 93, roughly? 93 plus 0.3 times father's height. So now we're back in the world where we have just one variable trying to predict another. Now I could also plug in 66 inches for the mother's height and look at all the mothers who are the same height to the nearest inch, and they're 66 inches tall. So that would be 9.2 plus 1.4 times 66, which is, somebody help me out here, what's that? About 87, maybe, or 97? Well, we can do that easily in R, right? But notice that what we get is what's changing, or we get a different intercept, but what's staying the same for each one of these? Whether you're 60 inches tall, or the mother is 60 inches tall, or the mother is 66 inches tall, we're getting a different intercept. So in one case, it's 9.2 plus 1.4 times 60. And in the next case, it's 9.2 plus 1.4 times 66. So the difference is about 8 ounces. But then it's plus 0.3 times father's height. So what stays the same each time is the coefficient for the slope. So yes?
Would that estimate a higher error or less error?
Higher or lower than?
The previous one where it was just based on mother's height?
Oh, we're going to get there. Yeah, we're going to get there. Yes?
So would it be nice to have like a three-dimensional regression plane?
Not necessarily. I mean, so that is exactly what we're doing, is we are in multiple dimensions now. That's exactly right. But it's hard to see in multiple dimensions. And so the point I'm trying to get across is that if we take any slice where we fix mother's height, it says that the relationship between birth weight and father's height should be the same in terms of the slope of the line and how you would go about with a father's increase of height by 1 inch increases the baby's birth weight on average by 0.3. And it's hard to see that in a three-dimensional figure. But that is what's going on. So what I have here is I've looked at 4 different groups of moms. 60 inches tall, 62 inches tall, 64 inches tall, 66 inches tall. I've taken slices of the data where the moms all have the same height to the nearest inch. And then I look at the relationship between birth weight and father's height. And what we want to see, and what I've put on here is the regression line that we fit, which has a 0.3 slope. And the intercepts, you can see the intercept changes. It's getting, the scales are the same for the y-axis as we look across, And you can see the intercept is rising, but the lines are parallel to each other. So that's what's going on when we add a second variable and are doing a linear fit to the data. It's saying that if we look at any subgroup where one variable is held constant, then the relationship between the y, the birth weight, and the other variable, father's height, should be the same across all these subgroups, with the intercept changing, but the same addition of 1 extra inch in father's height increases birth weight by the same amount. Okay? All right, what do you think about that regression? What do you think about those lines? They sure do. They look almost flat. It's 0.3. And so a question we might ask is, do we really need father's height here at all? And so when you start building these models, we so far have only looked at what's the single best predictor of birth weight. And we compared the RMSE error for all these one regressing birth weight on one other variable. Now we've regressed it on 2 variables, and we're starting to wonder whether it's worth including father's height or not. So one thing we can look at is the root mean square error from the regression for these 2 models. And we notice that they're virtually identical. Again, this comes out of R. And we might ask ourselves, is that 0.3, is it really essentially just 0? And all we're seeing is sampling fluctuations. So we can do a hypothesis test, and R gives it to us automatically. It looks at this coefficient, looks at all of the coefficients, but in particular we're interested in this one. It was actually 0.285. And it computes the standard error for that coefficient. So what's the typical fluctuation that I might see in this? And it computes a hypothesis test. And that hypothesis test is this really, my hypothesis is that this coefficient is really 0. Any observed deviation is just due to chance. Here's the probability that a 0 coefficient would have produced an observed 2.853, and we see that that's a large probability. So that says that father's height's not really in the presence of mother's height. Father's height doesn't add very much. Okay? This coefficient is not significantly different from 0. So you're not gaining much by adding father's height here. So the crucial thing to remember is that that hypothesis test is conducted in the presence of mother's height already being in the equation. So there are really let's look at these 3 different fits. One is birth weight on mother's height, single variable fit, mother's height alone. The other is birth weight on father's height alone. And the other is birth weight on the combination of mother's height and father's height. And so we are looking at these saying which of these is the best model. And there's a trade-off between complexity and simplicity, which is hard to quantify in terms of hypothesis tests. We can look at scatter plots of the residuals to see if this sort of linear association is even appropriate, or just those scatter plots like I showed you before. But then we can also compare the root mean square errors, and we can also look at the hypothesis test for each of these coefficients. Notice that father's height alone gives a really different model than mother's height and father's height together. That's because it's saying, I only know dad's height. How do I go about using that to predict the baby's birth weight? This final one here says, I know both of these things. How do I go about using them? In this particular case, if we just look at mother's height, that coefficient is significant. If we just look at father's height, that coefficient is significant, the 0.7. But if we look at the 2 together, we say in the presence of mother's height, the father's height coefficient is not significant. Similarly, we could say in the presence of father's height, is mother's height coefficient significantly different from 0? And it is. So, let me stop there before we go on to smoking status. Dan, does this kind of answer your questions?
Yeah, it does help a lot.
Okay. Are there any questions from the rest of you? Yes, sorry, I didn't see you there.
Is the reason that they're not significant, or dad's height is not significant, because the dad's height might be related to the mother's height?
Yes, that's right. And we actually looked at that before, and we did see that, in fact, mother's height and father's height were correlated. That's right. So you're not getting a lot of extra information about from the father that you didn't already have in the mother. That's right. Yes? No, it's the same. It's the same way around. So, in other words, when we're doing these tests here, if we look at the second row, that test over here is saying, is mother's height significant in the presence of father's height in the equation? And so, even when father's height's there, mother's height is still significant. Okay. But as I was saying before, that doesn't mean that father's height's not useful. If that was the only variable that you had, we can use it. It's not a good a predictor as a separate solo variable in comparison to mother's height, but it's still useful. And then when the two are together, mother's height is doing a better job of sort of predicting than father's height. Okay. Now I want to do the same thing that we've just done, but with categorical variables. Before we took the smoking status and said, well, the mother either never smoked or she's smoking while she's pregnant. And we know that that variable actually had more levels than that. It was a categorical variable that had 4 levels. The mother never smoked. The mother smokes now while she's pregnant. The mother smoked once, but not now. And the mother smoked up until she became pregnant. So there are 4 different levels for this categorical variable. And we can try and fit birth weight to that more complex categorical variable. Birth weight tilde smoke, it's got to be a factor for art to understand that these are not numeric data. It's categorical data that's, in this case, nominal, not ordinal. And what comes out is, this is the way I've written it, is birth weight is 122.8 ounces. Start there. Now, then if the mother smokes now, subtract 8.7 ounces. If the mother smoked until she was pregnant, add 0.3 ounces. If the mother smoked once but not now, add 1.7 ounces. So you can take that sort of if-then equation and create estimates for each of the 4 factors, each of the 4 levels of the smoke variable. Those who are never smokers, you start at 122.8 ounces, and you don't add or subtract anything. So that's your estimate for the baby's birth weight. For those who are smoking now, you take the 122.8, subtract 8.7, and get 114.1 as your estimate. For those who smoked until they're pregnant, you get 123.1. For those who smoked once and not now, you get 124.5. And R also gives you a RMS error for this regression. And it's 17.83, which is smaller than any of the others that we've done so far. But we might want to ask ourselves, is the 8.7, minus 8.7, the 0.3 and the 1.7, are they significantly different from 0? Or is it really just the chance variation that gives us these numbers? And from the hypothesis tests that R gives you, you can see that the 0.3 and the 1.7 are not significantly different from 0, but the minus 8.7 is, which is kind of telling us that the moms who never smoked, their baby's birth weight compared to the ones who just quit right before they got pregnant, or right as soon as they got pregnant, that their babies' birth weights are essentially the same on average. How about putting the two together? So smoking's the single best predictor, but what about the mother's height and smoking? Okay. So now I've just reduced smoking to they never smoked, I'm just looking at subset. They never smoked or they're currently smoking. And this is the equation I get. So birth weight is 33.0 ounces plus 1.4 ounces per inch minus 9.2 if they smoke now. So that essentially, if we say, okay, well, how does that work for those who are smoking and those who never smoked? Well, for those who are non-smokers, that's 33.0 plus 1.4 height. For those who are current smokers, it's 23.8 plus 1.4 height. So just like before, when we fixed the mother's height and looked at the equation for birth weight on father's height, now we're saying, oh, let's look at the group of non-smokers and let's look at the group of smokers and see how birth weight varies with mother's height. The slope stays the same, the intercept changes. You're doing this in your homework assignment, but from a brute force hand calculation way. This is how you could do it in R. I'm not expecting you to have done this for the homework that was due today, but this shows you how you can do it in R. And so these two lines have different intercepts but the same slope. And we can plot them together. I've jittered the data so that you can see more of the points. I've colored the never smokers green and the smokers blue. And you can see how, sure, there are green dots really low, but the bulk of the green dots are higher than the bulk of the blue dots. And these are the two lines. The one for the predicting birth weight from mother's height for the never smokers and predicting birth weight from mother's height for the current smokers. And they are parallel. And you're doing something very similar with gestational age. Okay? So the root mean square error for this is 17.26, which is the smallest of all that we've seen so far. So whether we're looking at mother's height and father's height together, we saw we don't gain much by adding father's height. But if we look at mother's height and their smoking status, we do better than if we look at mother's height alone or smoking status alone. And there are complications for deciding how many variables to keep adding. You will continue to reduce the root mean square error as you add more variables. So we have to be a little bit careful with just making more and more complex models. And there are ways to penalize for adding lots of variables, which we're not going to get to. All of these coefficients are significantly different from 0. So in summary, here's just an example where we have now 3 explanatory variables, x, z, and w. We're trying to predict y. So this is all just in terms of notation, whatever x, z, and w might be. When we fit a model that says y tilde x plus z plus w, what that's saying is if I hold any two pairs of explanatory variables constant, x and z, and then I look at the subgroup that defines, and I see how does y vary with w, it says that linear model has the same slope no matter what the x, z values are. The hypothesis tests, in this case, they're saying, excuse me, is w really needed in the presence of x and z? So if I am already predicting using x and z, does w add anything extra? Is the coefficient for w significantly different from 0? And the last is that we can compare models by considering the root mean square error for the regression line, but we might have to adjust for the number of variables, which is beyond the scope of what we're doing here. So it's a bit of an art/science in terms of how you go about choosing the best model. There are trade-offs between complexity of your model, looking at the reduction in the root mean square. is this really a linear association? Do I have enough data to be able to confirm that I've got the same linear association across all subgroups of my data? And that's it. So hand in your homeworks, 395 Evans, by, if not now, by 5 o'clock today.